So it's visual. Am I audible? And the slides are this board is visual. Okay, fine.
Yes, sir. Yes, sir.
Fine, fine. Thank you. So in morning we have discussed this state space averaging technique, right? Now let's go to another technique, and we have seen that how we can use this technique to obtain different transfer functions. Now let us quickly see this average switch modeling technique. So basically in average switch model, like we have this converter, this is V in, this is V out. Yes, so this is the converter. This is output, this is input. We have one mode, right? This is a linear equation, and we write it state space model. State space model. And when switch is off, then also we have one state space model. Now, after that only we average it. But in this techniques, what we do, rather, but in individual models, in the individual, we try to average the switch. We try to average the switch. So, what is the meaning of averaging? Average the switch means that we try to find what is the switch voltage and switch current. Okay. So when switch is on and when switch is off, in that case, we average either the switch voltage or switch current, and then get the linearized switch. Then replace this switch with its linearized model. Then we replace this switch with its linearized model. Now we know that this switch was creating the variable state system in converters. Now switch itself has been modeled with the help of linearized elements, voltage source or current sources, or maybe some resistances. Then our entire system becomes linearized, and after that we apply this KVL, KCL, and obtain the desired models, right? So in order to learn that how does it work, we directly take this buck converter example. So let's say again we are considering a ideal buck converter for simplicity. So let's say this is IC, I node, this is IL, this is switch. So we are denoting switch voltage, switch current. This is diode current, and we are denoting this to be, let's say, diode voltage. In this case, step one is obtain the average model of switch and diode. So basically, a diode is also kind of switch. So we consider diode to be as a switch. So what we do here, when 0 to DT period, which is on, then what is the converter model? This converter model is like this. The converter model is like this. When switch is off for DT2, for DT to T period, then our converter model is like this. This is your switch, right? So in this case, this is the switch current, and this one is switch voltage VSW. Similarly, this is the diode current, which is 0 in this case, and this is the diode voltage. Similarly, here this is the switch current. When switch is off, that is the 0. This is VSW, switch voltage. This is diode current, which will be having some value, and between these points, this is the diode voltage, which is 0. So like that, we are now interested in diode voltage, diode current, like that. So first step is obtain the average model of switch and diode. So before obtaining average model, what we do? Individual mode, maybe there are again 2 mode, 3 mode, 4 mode, 5 mode, depending upon the circuit configuration and its working. So here 2 modes, right? So in mode 1, now I am not writing inductor current or capacitor voltage as the previous one. In previous case, we used to consider states. Now in this case, we are not considering any states. We are just considering the switch current and switch voltage. One, your VSW of T, switch voltage is 0. What about switch current? Switch current is going like this, and this is same as inductor current. So this is same as inductor current. Okay, so this is switch volt, switch current. What about the diode voltage in mode 1? Because diode voltage VD, this will be the diode voltage will be minus V naught. No, not minus V naught. This will be minus V in. This will be minus V in. You can see here, this is the diode. The voltage across this will be same as minus V in. What about the diode current? Because diode is not conducting, so diode current will be 0. So that is our step 1 part in mode 1. Now mode 2. What about mode 2? So in mode 2 means switch is on, switch is off. Mode 2, what is the VSW? VSWT, that is some value. And what is that? This input voltage, now this is shorted, so it will be same as V in. V in. Now what about ISW? In this case, ISW is 0 because current will not flow through the switch is on, switch is off. Now what about the BD, diode voltage? Because now switch is on, diode is on, means switch is on means diode is on, and the voltage across this diode will be 0. What about the ID? ID is this current, and this is the same current which is flowing through the inductor, so ID will be IL. So this is how we have written the switch voltage, switch current, diode voltage, diode current. Now next step is to average it over one switching period. So we know that this is valid for D into T period, this is valid for 1 minus D into T period. Okay. Now if this is valid for dt period, this is valid for 1 minus dt period, and we want to find the average model of switch and diode, then what we do? We multiply this with dt, this with 1 minus dt, take average. What model It means if I take average of this, so average of VSW, this average will be 0 into D plus 1 minus D into V in. In this case, this will be 1 minus D into V in. What about the ISW average? ISW average will be D into IL. D into IL average. What about VD average? So obviously, all these are, as of now, these are function of time. Is also function of time. VD average will be minus D into V in. What about ID average? ID average will be, this is 0, so 1 minus D into IL average. Step 1, what we have done, we have find out the averaged behavior of this. Now, similar to previous one, this D is also function of time, this IL is also function of time. So two equations are there. It means this model which we have obtained, this is not linear, this is non-linear. This is averaged, but this is not linear. So we have to linearize it. We have to linearize it. So in order to linearize it, what we do, I just need this model. So in order to linearize this, next step is, step 2 is linearization of averaged model by introducing small perturbation. Okay. So this was our average model. Now we will introduce these perturbations. So what is the possible perturbations? VSW. This we will represent of T. This we will say its state value plus some small signal perturbation. Right. Similarly, ISW, some small signal perturbation in this. Similarly, this diode voltage we have. So its average value plus some small perturbation. We have diode current. So its DC value plus there is some perturbation, right? So all those things. Similarly, now we have V input. So V input plus perturbation in V input. Similarly, we have inductor current, IL average. So that is a capital IL plus perturbation in this. Okay, similarly, we have, so whatever variable we have, we will take perturbation in every variable. Okay, now we'll put these perturbations into this averaged model. So what we get from here, we will get first equation VSW plus Vs perturbation, that is equal to 1 minus D minus D cap. I am just removing T subscript as of now to make it simplified. 1 minus D minus T cap, and instead of this V in cap. Right, so we can simplify it. 1 minus D minus 1 then plus 1 minus d v in cap, then minus v in d cap, then minus d cap v in cap. Right? This is the one equation. Now we can see here that this equation is having this term to be second order. So in order to linearize, what we can do, we neglect these higher order terms. We neglect these higher order terms. We neglect this term, which is very small because perturbation, then perturbation in V in perturbation in D, both are small. Small into small will be further small. So easily we can neglect without affecting much to these dynamics, right? So this is first equation we got. Now second, this one, ISW plus ISWT, that is D plus D cap, IL plus IL cap. Simply multiply DIL, okay, plus DIL cap plus IL D cap plus IL cap D cap. So again, if I want to simplify this, then I will neglect these terms to be 0. Okay, I will just neglect these terms. The third one, this one VD. So this is VD plus VD cap of T, that is equal to minus D plus T cap, then V in plus V in cap. Simplify it. So minus dV in minus dV in tilde minus V in D tilde, then minus D tilde V in tilde. So again, in order to simplify, in order to make it linearize, we just neglect these equations. Then the fourth one, ID. So the ID plus IDT 1 minus D, so that is 1 minus D minus D cap IL plus IL cap. Let us simplify it. So this is 1 minus D into IL minus 1 minus D IL, then minus IL D cap. So this will be plus, this will be plus, right? Minus D cap IL cap. Is it okay? Any doubts so far? Again, in order to linearize it, we will neglect it. So 1 minus D IL. Okay. So these equations we have obtained after linearization. Now these four equations are linearized. So one thing we can observe here that this is DC part, this is perturbation term. Similarly, on the right hand side, this is the DC part, this is perturbation terms. Similarly, here DC part, perturbation term, DC part, perturbation term, right? So in next, next step, we can separate out this linear model and small signal model. But before that, I will just before we go for the next step, what we are going to do now? We have obtained the relation of voltage and current in the switch in terms of inductor current, output voltage, or input voltage. Yes, we have obtained in those terminology. Now we will replace our original circuit. We will replace our original circuit with the help of these linearized models. With the help of this linearized model. So a switch can be replaced either by this voltage or by this current. Similarly, diode can be replaced by this voltage or this current. So we take one from each. We take one from each. If we are taking voltage for the switch, then we will take diode for the current. If we are taking switch, the current for the switch, then we will take a diode for the voltage. So let us take we take voltage for the switch and current for diode. So what was our original circuit? We had one one, and this is our inductor, this is our capacitor, and this is our load. This was our original circuit. Okay. Now we are having this across this switch. We have this term ISW and VSW. Similarly, here this ID and this VT. Now, what we are going to do, we are representing this switch VSW with its voltage. So, what I do, I just remove this switch such that its terminal behavior does not change. Its terminal behavior does not change. So, what I am doing here, just let me take this red one. I am replacing it with switch. It means I have to respect its terminal behavior. So I will put here these equations VSW plus VSW. It means and this is the constant, and this is constant. You know, 1 minus d into Vin. So Vin is fixed, d is fixed. This is constant, independent. But this is dependent. This VSW cap. This is dependent upon variation in input voltage as well as variation in duty cycle. What I do, I have two sources. One is independent source and another is dependent source. This independent source value is VSW, which is given by 1 minus D into Vin, and this dependent source is given by VSW cap, which is nothing but this 1 minus D V in minus V in D cap. This one minus D V in cap minus V in D cap. So this is this VSW. Now similarly, this diode I'm going to replace with its current equivalent. Okay, so if I represent this diode, so this I need to create diode equation with the help of this current source. Now this is the current source, two current source. One is independent, another is dependent. So what was the direction of our actual diode from down to up? So what we will do here, we will connect two current source, keeping the direction same as the original direction of the diode, and we'll add them up like this. So this is ID and this is capital ID, where ID is given by 1 minus D into IL, or ID cap is given by 1 minus D IL minus IL D cap. So now that way we have obtained this circuit. Now this circuit is called linearized large signal average switch model of DC to DC buck converter. So in this step, we have obtained the linearized model. Now you can see that this circuit is no longer a switching circuit. It's a linear circuit now. The switching part has been replaced by the linear elements, right? Linearized elements. Now in next step, what we can do, we can segregate the steady state part and we can segregate its small signal part. So how to do that? So for that we go to new page, next step 4, let's say, separating or obtaining DC model and AC model. So for DC model, For convenience, let me crop this and put on next page. Let's say this one. This is our model. Now from this model, we want to obtain the DC model. Okay. So one more thing I want to just tell you that remaining things will be like this is the small signal, large signal model. So this V in will be V in plus V in tilt. This IHW will be IHW plus IHW tilt. Right? These two are same. Now this is ID, and what is the voltage across this? VD plus VD tilt. Similarly, all those things. This is output voltage, V output plus V output tilt. Similarly, this current through capacitor, this inductor current will be IL plus IL tilt, like that. Now, if I am obtaining the DC model, then what I will do, I will put perturbation terms to 0, 430 or 415 आ जाना 415 सवा चार में. So perturbation terms to be 0. Now, if I put perturbation terms to be 0, what is the meaning of this? That whatever this V in cap, I in cap, whatever it is coming, that should be 0. So let us start. So what will be the input side? Input side, there will be V in. Now, this is okay. Now, what will be the current? ISW. Then here, this perturbation part will go away. Only independent source will be there, plus minus VSW. And what will be here? Only capital ID, then what will be for inductor? Now, if I take the DC model, then how inductor will behave? You know that inductor is S into L. So frequency 0, inductor is shorted. So this will behave as a shorted. No inductor will be shown. And what about capacitance? This is represented as 1 upon SC. So if frequency is 0, then 1 upon SC is infinite. It will be open circuit. So this will be open circuit. And now this is your current R, and this is a voltage across this V0, and this current will be IL only. So this is your steady state model or DC model. Remember, we are just doing for buck converter so that it can be easily explained, but the same steps are followed for any type of converter. Now we will analyze this circuit. So let us put simply the KVL over here. So we'll start from here. We'll go through this. We'll put KVL in this V in. So what is KVL? Minus V0, that should be equal to 0. Now the value of VSW, we'll see from the previous slide. Value of VSW is 1 minus D into V in. 1 minus D into V in minus V0, that is equal to 0. So simplify it, V in minus V in plus dV in minus V0 equal to 0. And from here you get V0 equal to dV in. Okay. So this is the output voltage, and this is expected also. So we get one relationship from here. Another relationships we may get when we apply the KCL at this point. So this is first relationship. Second relationships we get when we apply KCL. So what is the KCL? That is ISW and ID both are forming ISW plus ID. Both are forming IL. So what do we get from here? Anything useful? ISW and ID. So you know ISW is D into IL and ID is 1 minus DIL. So you can see that this is also matching. This equation is matching. And directly we can see from here that this I naught is equal to IL in steady state, right? So these equations or this information we get from here. Now, if we talk about it's a small signal model, it's a small signal model, so which is very important as well. So just a minute, please. Okay, so for getting a small signal model, we put DC term, DC term, and you can see 0. So, so in that case, that is what if you are putting DC term stage, you start from here. This is V in cap. Now after that, this is the DC that will go away. Go away. Dependent source is there, which is having VSW cap. After that, we will come here, and what is the current? ISW tilde, ISW tilde. After that, this portion. So this portion we will keep only this perturbation term. So this is the perturbation term which we keep current source. Direction will remain same as actual diode, and this is ID. Okay. Now after that, this will be IL cap, and the this inductor. Now this inductor will be as it is, having the value SL. Okay. Now this capacity, because we are doing small signal analysis, which is done at different frequencies, this will be 1 upon SC, and this load resistance which remains same in both case AC and DC, and this is your perturbation voltage, right? So this is your I node of S, this is IC of S. Now we get this linearized small signal model. This is called linearized small signal model. Okay. Now this small signal model is used to obtain various transfer functions. So now this let us write these two terms also in this VSW. So what was the VSW? VHW. This one is थोड़ा सा crop करता हूँ. Just temporary I'm putting it over here. So this VSW is this is 1 minus D V in cap minus V in D cap, and this ID is 1 minus D IL cap minus IL D cap. Okay, so this is two things we needed here. We can delete it now. Okay. Well, so now with the help of this small signal model or this linearized model, we can obtain all these transfer functions. So how to do that? Let us see. Let us see it. Okay. We will obtain various small signal models. Small signal models with the help of this. So we will just write the KVL equation, right? So we will write KVL equation in this loop. We will write the KVL equation in this loop. So what is the KVL equation in this loop? So this we start with V in of, I'm just removing these terms S and all. V in minus VSW minus SL IL cap minus V node of S or V node equal to 0. This is the very first equation. This is the very first equation. Similarly, I can apply the KCL over here. So this KCL gives us ISW equal to ID plus IL, ID plus IL, ID plus IL, right? And the next equation is that this one, this I naught plus IC that is equal I naught plus IC that is equal to IL, right? Or you can say from here, if I consider this to be one single impedance, then I have one relation V node equal to IL into this impedance, IL into this impedance. And what is this impedance? If I say this to be Z naught, then what is this Z naught? R in parallel with 1 upon C. So this is R into 1 upon SC, R plus 1 upon SC. So it comes out to be R upon 1 plus SRC, right? So that is our Z naught. Okay. And this is the relationship we have, IL into Z naught. Okay. Now let us simplify this one first. So from here, what we are getting, V in minus VSW. So VSW is 1 minus D, V in cap minus V in D cap. This is VSW minus SL IL minus V naught equal to 0. And from here, if you simplify this, so this V in will go on. So this is 1 minus D into V in cap minus V in into D cap minus SL IL cap minus V naught, that is equal to 0. This is the R1 equation. Okay. Another equation is that this one, V naught of this equal to Z naught. Okay. Now, let us say we want to find the relationship between, we want to get this transfer function V naught of S with respect to D of S. For example, let's say I want to get this transfer function. So when I am finding the effect of D on V naught, that time I will not take into consideration the effect. I will say this perturbation in V is divided into 0. So that time what this equation 1 becomes? This 1 becomes 0 minus V in D cap minus SL EL minus V naught equal to 0. Right or not? Yes. So this becomes my 1A. And this equation V naught equal to IL into R upon 1 plus SRC. That equation is always valid. So this is my equation number, let's say 2. Right? Now I want a relation between V node and D, and I have equations which have D, IL and V node. So what I can do, I can eliminate IL from here. It means if I write IL equal to V naught into 1 plus SRC upon R. So this is from this. and I put IL back here. So what do I get? I do get 0 minus V in D cap minus SL. Now this is V naught 1 plus SRC upon R, okay, minus V naught equal to 0. Let us simplify this. So if I simplify this, then okay, something wrong here. No. Just wait a minute. Let me check if something wrong is here. So minus sign, why it is coming? One minus sign issue is there somewhere. Have to check it. This should be plus. Where did I mistake? This should be plus. Okay. This one. V in minus. Yes, yes, yes. So when this is V in minus V as cap. So when we are putting this term will be positive here, right? Yeah. V in minus 1 minus d V in cap and minus minus plus. So this term will be plus. This will be plus. Okay. So this will be plus. Yes, I'll tell you. I'll tell you. Okay. So let me correct it first. Okay. So what I said. Okay, I think you understood till this point. In the previous slide, we have obtained this model. Now, using this model, we want to get different transfer functions. Now, what is happening here? We have one variation in duty cycle, another variation in input voltage. So, for this equation, in general, we wrote this. For this figure, in general, we wrote this equation simply by putting KVL. V in minus this voltage source, which is VSW, minus drop across this inductance minus SL into the respective current, and then this voltage minus V naught. So this equation is clear. Okay. Now the next equation is that important equation V naught equal to IL into Z naught. So let's say this current is coming from here IL, and this entire impedance is Z naught. If I multiply this IL into Z naught, then I will get V naught. This equation is clear. Now what is the Z naught? Z naught is R in parallel with 1 upon SC. So R in parallel with 1 upon SC, R both are in parallel, C and R. So R into 1 upon SC divided by R plus 1 upon SC, we get this. This is Z naught. Now we are simplifying this equation further. In general, right now we have not done anything to be 0. So V in minus, we are putting value of VSW, which is this one, 1 minus D, V in cap minus V in D. So minus 1 minus D, and this minus and outside minus, this becomes plus V in D cap. Okay. Then minus SL IL cap minus V naught cap equal to 0. So this equation is true. Now, because this is V in, this is minus 1 minus d V in. So if we simplify, this will be d into V in plus V in d cap minus SL IL cap minus V naught equal to 0. So this becomes our final equation. And the another equation V naught equal to IL Z naught, that is always true. Now, with the help of these two equations, we want to get different transfer functions. Now, I want to get a transfer function V naught upon D. It means what is the impact of variation in output voltage if duty cycle is varied. So in that case, what we do, we put other perturbations to 0, because kind of superposition theorem when we use, we keep only one source active at one time, right? Now there is two different input sources, one is D, one is V in. So we have to keep V in to be 0 to see the effect of D. If we are seeing the effect of V in, then we have to keep the D to be 0. Okay. So that's the reason in this equation, when we are we are trying to find out this one. In this equation, we have V in to be 0. V in means variation in V in, that is 0. So this term has become 0. Then remaining we will take as it is. And second equation also will take as it is. Now we have these two equations, equation 1a and equation 2. With the help of these two equations, we need to find V naught upon D. Okay. Now this equation has three variables. One is D, another is IL, third one is V naught. Right? We will eliminate IL because IL is not to be used by us. If I eliminate IL, it means I can keep this equation like this. So I'll put IL value over here. So this is V in D cap minus SL. IL value I am putting here. This is IL value minus V naught equal to 0. I will simplify this. So this is V in D cap. I will take both values both sides. So V naught is common. SL 1 plus SRC upon R plus 1. Okay, further simplify it. Let's say V naught. So if you simplify this, this will give you SL plus S square RLC plus R divided by R. Okay. So if I want to find V naught upon D, and denominator with with RLC, then in numerator I get V in upon LC divided by S square plus divide this by RLC, so it will be 1 upon RC into S plus 1 upon LC. And you know that this same equation we have obtained using state space modeling. So where was that? You can see Vg upon Lc S square plus 1 upon RCS plus 1 upon Lc. So same equation we have obtained through this way. Now the method is different. So this is, we wanted to find V naught upon D. If in the same we want to find IL upon D, let's say, then what we will do? We will just eliminate V naught from here. So we will put V naught over there. So what we get in that case, V in D cap minus SL IL minus IL R upon 1 plus SRC. We'll put V naught value here equal to 0. Right? So IL to with that side. So simply IL you take this side, so it becomes SL plus SL plus R upon 1 plus SRC. Right? So we simplify it further. So this is SL plus S square RLC plus R upon 1 plus SRC. So if you further simplify this, let me simplify here itself. So this is IL upon D unit. IL upon D unit. It means V in 1 plus SRC divided by S square RLC plus SL plus R. You just divide with the help of RLC. So this is V in upon RLC 1 plus SRC divided by 1 plus 1 upon R, no, S square plus 1 upon RC into S upon plus 1 upon LC. So this is IL upon D. Maybe in morning we derive something. This one, yeah. This one we derived Vg upon L. So you, if RC you take inside, if you take RC inside here, then you will get V in upon L S plus 1 RC divided by this term. So V in upon L S plus RC. So you can see here that same term, the same term we are getting there. Okay. So this is the first one. Now if we want to get the second, then what we need to do, if we want V naught upon Vg, then we can state, if, let me see this equation of the new page. If we want a transfer function, V naught upon V in, then we have to set D to be 0, right? So if you are setting D to be 0 over here, here in this equation, then what you are getting, D into V in cap, you set it to be 0 minus SL IL cap minus V naught equal to 0, and another term is V naught equal to IL Z naught. Now you need V naught upon V in, so you eliminate IL, put it back there. So this is dV in minus SL V naught upon Z naught minus V naught equal to 0. Right? You replaced IL by V naught upon Z naught. So dV in is upon SL plus Z naught. Now you put the value of Z naught. What is that? This one, R upon 1 plus SRC, R upon 1 plus SRC. So you get D into R upon 1 plus SRC divided by SL plus R upon 1 plus SRC. SRC will cancel out, so it will be D into R. This is S square RLC plus SL plus R divided by the RLC both sides, D upon LC, then S square plus S into 1 upon RC plus 1 upon LC. So this is what V naught upon V image. Okay, so that way we can get the transfer function using this particular technique. So any doubts so far, please let me know. So any doubts so far, please let me know. If no, then how to designate current and voltage to 3 switches. You take any one current and any two to be voltage. If there are 3 switches, then if there are 3 switches, then you designate VSW, ISW. In each mode, get the current and voltages across each switch. Okay. Note the time interval of each mode. If there are more than 2 modes, then we will get the linearized model for each switch, its current and voltage for each switch. Now we replace that switch by its linearized model, either voltage or current. Then once it is replaced by its linearized model, then we can get the overall large signal model of linearized model, and then we can, same process again, DC model and AC model, we can segregate it. Okay, so I think I gave answer to you. I will take 2 minutes break, and we'll again continue the same lecture. So, So are you able to see some slide over here? Are you able to see some slide? Any slide are you able to see on screen?
No, sir. No, sir.
No.
No.
Okay. Acha, not sure. Just a minute, please. Are you able to see now some slide? What is written? Buck converter design, right? Bhupesh, what is written on the this slide which is being shown to you?
Sir, parameter design DC-DC buck converter.
So it's on full screen now. It's full screen.
No, yes, sir. Yes, sir.
Okay. Okay, well, so far we have discussed that in detail how to design the converter parameters, then how to model it, right? We have taken everything to be ideal. Then, like for boost converter, we have seen the impact of this consideration of non-ideality on the performance. That even at duty cycle d equal to 1, the output is expected to be infinite, but it becomes 0. And in other words, we say that as duty cycle increases, output increases, and then it becomes maximum. Then it starts reducing, right? So now, just a minute, 1 minute, please. So now we will see the impact of this parameter design on impact of these non-idealities on parameter design. Just I am resharing it to you. Online has this problem which just a minute, please. I'm facing some issue with the slideshow. Are you able to see now? Rupesh?
No, sir, screen is not sure.
Screen is not shared. Now? Now it's visible? Okay, visible. Fine. Okay, so just quickly see what the impact of these non-identities are there on the converter's performance. This is buck converter. So what are the possible non-identities? Like we have a switch. So when switch is on, we can have this uh, RSW, which is the switch on resistance. Okay, when on, then off, then we will have zero resistance, infinite resistance, let's say. Similarly, this diode can be represented with this. When it is on, it can be represented with this. It's a diode voltage. It's diode resistance and this forward voltage drop. Similarly, this inductance can be represented with RL and RC. So like that, we represent this. This is ideal buck converter, and this is non-ideal buck converter. So this is everything is there in this paper. You can refer this paper. So now we will try that how this design and everything steps remains same, but the analysis impacts a lot on the performance. So we have considered all those non-idealities in the converter, and now we will proceed for the its analysis. So analysis will be same way: switch is on, switch is off. Now when switch is on, then I have represented this switch A resistance, and obviously this diode is not there now. This is open, so this is not there. Now this inductance is represented this way and this capacitance is represented this way. We have written again the inductance voltage, capacitor current, and output voltage equation, standard three equations. When switch is off, then also we have represented the inductor voltage, capacitor current, and output voltages. So switch is on, we have done analysis. Switch is off, we have done analysis. Even these three equations we will see just that will be used for modeling purpose as well. Now the next part is sorry. So the next part is its DC. So next part is its DC analysis, steady state analysis. So in steady state analysis, what we do volt second balance and we do volt second balance. First is the volt second balance. So through volt second balance, we got this equation, right? The inductor voltage into dt plus inductor voltage in off condition into 1 minus dt. So we get this equation. Now this equation is there. Second analysis we do capacitor charge balance, right? So when we do capacitor charge balance, we get this relation. Now those two relations we have obtained, right? Now you can see that if we replace IL equal to V naught upon R over here, then where is the next slide is not again. Slide is not moving right. Okay, so fine. So next is if we are putting that and we are simplifying it, then our output voltage is coming like this. Now previously what we have seen that always we know that output voltage of DC to DC buck converter is given by V naught voltage drop, RL is the ESR, RL is the switch and diode resistance. Due to these resistances, there is voltage drop, and due to that voltage drop, what is happening? The actual voltage across the load is lesser than dVg. So if you see this equation and this equation, so this because this term is 1 plus something, so definitely this entire voltage is less than d into Vg. So what is happening here? If you say, let's say you have designed one buck converter, 10 volt input and output, input is 10 volt and output is 5 volt. Duty cycle is 0.5 definitely. So with this ideal case, you will get 5 volt output. But here what is happening, if you keep the duty cycle to be 0.5, right? And then you put this duty cycle 0.5 and then if your input is 1 volt, but what will happen? Some voltage drop will occur across these different elements. Finally, the output voltage will not be 5 volt. It will be somewhere 4.8 volt and so on. So it is not 5 volt. So it will differ. So in that case, what we need to do if we want exactly 5 volt, we have to increase the duty cycle. We have to increase the duty cycle. So how much duty cycle we should increase? To know that, what we do, we reverse calculate D from here. If we calculate D from here, then we get this expression. And what this expression suggests, that D is greater than 1. That actual duty cycle in non-ideal converter, that should be greater than the D ideal. It means D ideal is 0.5, so actual duty cycle should be greater than 0.5, maybe somewhere 0.55. So if I'm putting 0.55 duty cycle, then my input voltage is 10. So ideally I should get 5.5 volt, but 0.5 volt is, let's say for lump sum, it is being fed to the non-idealities. So ultimately I will get the 5 volt. It means my converter should get or should be operated at this increased duty cycle, right? So that is the first thing. Now second thing is that what will be the impact? What will be the impact on it is automatically. What is the impact on other parameters? So if you see here, we have shown these graphs, duty cycle versus output voltage. So normally output voltage V naught is D into V. It is nowhere having resistance in this expression, so it should be independent of the resistance. But when you do actual analysis and find this expression, then you know that as R is increasing, then it will have, or R is decreasing, it will have impact on output voltage. So if we plot this, then we can see the impact that as your R is varying, resistance is varying, the output voltage also varies. So that's why we need, I always tell that we need a control system. Why? Because if there is any variation in the load, then your output voltage will fluctuate. And in order to compensate that output voltage, your duty cycle should be recalculated. We have seen in the previous slide that duty cycle is depending upon R. So if load or duty cycle is also depending upon input voltage. If there is any variation in input voltage, then we should identify what is the new duty cycle requirement, and accordingly we should provide that much duty cycle. So that is possible only when we will feed it back, or we know that what is the variation happening in the output voltage. Okay. Now this also affect the inductor. So in ideal case, this is the inductor value for a buck converter which is designed, but in non-ideal case, this expression comes to be something different, right? And if you see this plot, then what it says that a particular duty cycle, the inductor requirement for ideal case and non-ideal case are different. So, and our actual converter is ideal or non-ideal. Non-ideal. Actual converter, practical converter is non-ideal. So it means we should, if we are accurately designing this converter, then we should told you previously we discussed that this capacitor voltage is the voltage same as appearing across the capacitor across this load. So if this is ideal, then whatever is the voltage across capacitor, same will be the voltage across the load. But due to this ESR, presence of ESR, the output voltage ripple will increase. So actual output voltage will be sum of VC plus IC into RC, right? So if RC is, and you know that the nature of IC is like that, right? So if it is getting multiplied with RC and added in this, then ripple will further increase, right? So in order to design a proper capacitor, so yeah, it's already there in this these waveforms you can see. This is the nature of capacitor current, and these three waveforms are here. One is this one is your voltage due to ESR. This one is your voltage due to capacitor itself. So actual output voltage will be this one, this one, right? So it is having some more ripples. So in order to mitigate this, we have to properly design the capacitor, and for that purpose, what we have done in our work, that we have developed this total analysis, and we found that the new value of capacitor should be found with the help of this formula, and which is taking into consideration this RC, right? This RC ESR, and depending upon this RC, value of C will be decided. Now this RC also has its optimum value. What can be the maximum value of RC which is allowed, so that a ripple across the load is within the range? So so here you see it. Second, creating problem. This impression is coming from previous slide. So let's say, for example, we have these parameters where input voltage is 20 volt, output voltage is 12 volt, and so ideally, what should be the duty cycle? 0.6, but we have considered all elements to be non-ideal. We have switch volt, diode volt, right? ESR of inductor. So when we put all these value of ESR, then we find that this duty cycle required is not 0.6, it is 0.6415. If this is the duty cycle, then I will get 12 volt when input voltage is 20 volts. Similarly, I found out the with the ideal things, this inductor value is 448 microhenry, but in actual it is 490 microhenry. Similarly, this RC2 max, as I said, maximum value of ESR with this capacitor is 0.24 to get the 1% ripple. If it is more than this value, then you cannot get 1% output voltage ripple, right? Then further you need to change the capacitor value. Similarly, the ideal value of capacitor is 25 microfarad, but in actual, to meet this requirement, we have to increase the capacitor value to 50 microfarad, because ESR is there in picture now. So to mitigate the ripple due to ESR, we have to increase the capacitor value. So that is 50 microfarad we need. Okay, so few are the results which shows this study here. you are seeing here simulation as well as hardware experimental result that if you are giving 20 volt input and keeping duty cycle to be, let's say, 0.6, with 0.6, then what is happening? You are getting the output voltage which is less than 12 volt, right? But if you are increasing duty cycle to new value, then your output voltage are now settling to 12 volt. You can see here as well, right? It means that based upon the components being used, we know their ESR values, then we can calculate the exact duty cycle. So this is being done in open loop, but in closed loop, who does it? Controller does it for us, right? Similarly, if you see okay, similarly, if you see now we are using a capacitor of 50 microfarad this purpose. And if ESR, so what is the 1% of, so we our output voltage requirement is 12 volt. 1% ESR we allowed, so that is 0.12 volt, that is equal to 120 millivolt, right? Now, in case of ideal capacitor, we need 25 microfarad, right? But in case of practical, we used 50 microfarad. So all these things are being discussed with a capacitor of 50 microfarad. Now, because you have used a capacitor size, now RC is 0. In simulation, we can keep RC equal to 0, but not in hardware. So this is the ideal capacitor. So for the ideal capacitor, what should be the ripple? This is the same as VC. Now, what is the ripple coming into VC? So this VRC 0, so both are same. This is 0.06 volt only. Why it is becoming half of this design? Because capacitor being used is double. Right. Now, if I keep capacitor value to be 50 microfarad only, and I increase its ESR to 0.1, then my output voltage ripple is 0.075 volt, and 75 millivolt. So still it is within the limit. I can allow up to 120 millivolt, 1%, right? So this is also fine. Now, if I keep on increasing this ESR value, and let's say I reach to this value 0.2398, which is my maximum value, then what ripple I'm getting? 0.12 volt, 0.12 volt. That is 120 millivolt. Now this 120 millivolt is there. It means I have just reached to 1%. But if I increase this ESR further, that is, let's say, 0.4, greater than this value, then what is happening? My output voltage ripple is now 0.19 volt, which is 190 millivolt, and it is greater than 120 millivolt. So I am crossing the design limit. I am crossing now the design limit. So it means that is not the better design. User has said that I need 1% ripple, but you have used components such that it is giving more than 1% ripple. So it is not meeting the criteria. It means we have to redesign. We have to find good capacitors which is having low ESR value, then only I will make it. Okay, so that is the case. Now, I have some poor pure capacitor, or I do need this ESR value capacitor, whatever is available with that capacitor, you have to check it, right? So in hardware, let's say we found one capacitor with ESR 0.1, another with 0.4, same value of 50 microfarad. Okay, so now we are checking these results, and what we are finding that if it is less than the RC max, then our output voltage is 0.075 volt, and that is being measured. But if it is 0.4 ohm greater than the RC max, then our output voltage ripple crosses, and this is not as per the design criteria, right? So that way we see that importance of considering these ESR values in our uh, analysis. That is very important, right? Now this is what is time, 3:33. Okay, so we stop over here, and we will discuss on the next class whenever I get the control aspects of this DC to DC converter. We have discussed design aspects, we have discussed the modeling aspects. Now we will discuss these control aspects in the next class. Also, I'll try to show in initial few minutes that how these non-idealities impact the modeling. Okay, so we'll see next class. So I stop here. Any doubt? We can take it, and then we go for quiz. If any doubt, please ask. So Anupam, are we ready with quiz? What is D dash? D dash is 1 minus D. Just for compact, to keep it compact expressions, we just try D dash equal to 1 minus D. Any doubt, please? Unmute me. Anupam, please unmute Mr. Nitish Verma. Yeah. EICT host, can you please unmute one participant?
Send the request to Nitish Verma.
नितिश जी, आप जी अनम्यूट अपने आप को. Nitish, are you able to unmute? नहीं, एक आपको रिक्वेस्ट आया होगा, उन्होंने दे सेंट रिक्वेस्ट टू अनम्यूट यू. हाँ, now you are in panelist. Yeah, you can unmute and ask.
Sir, in average switched model, what you have explained, in that you told us we have to consider switch as a linearized model of voltage and diode as a linearized model of current.
अपोजिट एक्चुअली उसमें क्या होता है ना, अदरवाइज वो दोनों को आप वोल्टेज या दोनों को करंट ले लेंगे ना, तो आपका कुछ लूपिंग का इक्वेशन लिखने में वो कॉम्प्लिकेट हो जाएगा. ले तो लोगे आप, कोई प्रॉब्लम नहीं है ना. फिर केवीएल
मतलब सर वो थंब रूल क्या है, मतलब अगर मेरे पास 3 डायोड हैं, 2 स्विचेस हैं,
कि
तो
आप
थंब रूल क्या रखूं?
आप केवीएल केसीएल लगाओगे ना, वो कंप्लीट होना चाहिए उस लूप में इजीली.
मैं जनरली अगर ये लेके चलूं कि मैं स्विच को एज अ वोल्टेज ही लिनियराइज मॉडल करूंगा, डायोड को करंट ही करूंगा, या फिर कनेक्शन पे डिपेंड करेगा. कोई पैरेलल है तो मैं करंट लूं तो वो ज्यादा अच्छा है, कोई सीरीज में है तो मैं वोल्टेज लूं
और
तो
मैंने
ज्यादा
दोनों
अच्छा है.
तरीके से करके देखा, जो आप कह रहे हो ना, दोनों कॉम्बिनेशन करके देखे. उसको करंट, स्विच को करंट भी करके देखा और डायोड को वोल्टेज भी करके देखा. तो उस केस में भी एक्सप्रेशन सेम ही आते हैं, है ना. बस थोड़ा सा सॉल्व करने में वो मतलब अलग अलग दोनों केसेस में डिफरेंट हो जाता है. फिर आपको वापस से कुछ और एक्सप्रेशंस रखने पड़ते हैं. मान लीजिए आपने उधर करंट ले लिया, अब आपको केवीएल लगाना है उधर, तो उधर फिर वोल्ट आपका करंट सोर्स तो कुछ काम ही नहीं आएगा. करंट के थ्रू जो वोल्टेज आना लेना current, the voltage as well as current as obtained through process. So both are valid.
अच्छा, एज पर मतलब हमें कितनी कॉम्प्लेक्सिटी को रिड्यूस करना है, उस हिसाब से हमें वाइजली चूज करना पड़ेगा. वो एट अ इंस्टेंट ही होगा कि क्या सर्किट है, वो क्या कह रहा है.
ट्रू, वेरी ट्रू. क्योंकि टर्मिनल बिहेवियर पे कोई चेंज नहीं आ रहा है, वो तो सही ही दे रहे हैं. बस टर्मिनल बिहेवियर हमारा सही होना चाहिए. बाकी आप सर्किट की कॉम्प्लेक्सिटी के हिसाब से किस तरह से उसको सिंप्लीफाई कर सकते हैं, अकॉर्डिंगली वी डू इट. फाइनल आंसर में कोई चेंज नहीं आएगा. बट
सर आपने क्या ये कितने किलोवाट्स की फ्रीक्वेंसी पे काम करा था अपना, ये जो आपके रिजल्ट्स थे हार्डवेयर के, वो कितने किलोवाट्स
सॉरी,
The switching frequency you have used in DC-DC converter, what result you were showing in your work. Hello.
नहीं दोबारा से बोलिए, आपका आवाज स्विचिंग फ्रीक्वेंसी से रिलेटेड आप कुछ पूछ रहे हैं, क्या पूछ रहे हैं?
What was the value of switching frequency?
20 किलोहर्ट्ज 20 किलोहर्ट्ज
अच्छा,
20 किलोहर्ट्ज।
so मतलब आपने जो कैपेसिटेंस है वो बाय करा था एक पर्टिकुलर ESR की वैल्यू का?
नहीं, हमने फोकस किया कैपेसिटेंस वैल्यू पे, है ना,
50 माइक्रोफैराड हार्डवेयर वाला।
हाँ, फिर उस पे जो भी वैल्यू जो भी ESR मिला, 2-3 तरह के कैपेसिटर यूज कर लिए, है ना, अलग अलग कंपनीज के, तो जो मिला वो उसके हिसाब से हमने सिमुलेशन में वैल्यू सेट कर दिया। मान लीजिए मैंने 0.1 किया है, तो 0.1 था तो 0.1 कर दिया, अगर 0.15 होता तो मैं उस पर टेस्ट कर लेता।
मतलब सेम इलेक्ट्रोलाइटिक वाले कैपेसिटर की वैल्यू ESR की डिफरेंट थी।
हाँ हाँ हाँ।
तो वो सर एक्चुअली वो मतलब आपने सेम मैन्युफैक्चरर से खरीदा था वाला कैपेसिटर की अलग अलग मैन्युफैक्चरर से, अगर आप याद है?
अलग अलग
तभी वो वैल्यू डिफरेंट है।
लैब में बहुत सारे होते थे ना, तो अलग अलग ट्राई कर लिए। एक और इसका तरीका अगर नहीं होना और आपको हायर का ESR, तो वो मतलब बहुत अप्रोप्रिएट तो नहीं है, बट आप एक बहुत कम ओम का रेजिस्टेंस सीरीज में कनेक्ट कर सकते हो।
हाँ, वेरिएशन
0.1 का है तो आपको 0.4 बनाना है, तो 0.3 और ऐड कर दो उसमें, तो थोड़ा इम्पैक्ट तो उसका दे ही देगा वो।
और सर आपने ये जो इसका फॉर्मुलेशन वगैरह करा है अपने काम में, वो सारा आपने स्टेट स्पेस एवरेज से करा है?
दोनों
एवरेज से दोनों से शो करके दिखाया है?
दोनों से करके दोनों के रिजल्ट भी सेम ही आते हैं, बट जस्ट हम ये शो करना चाह रहे थे कि अप्रोच डिफरेंट हो सकती है।
इवन वो बॉन्ड ग्राफ के थ्रू भी रिजल्ट सेम आए थे, सिग्नल फ्लो ग्राफ के थ्रू भी मुझे लगता है द रिजल्ट विल बी सेम।
ग्राफ मैंने यूज नहीं किया है, इसलिए मुझे उसका नहीं पता है कि उससे क्या आते हैं। वो मैंने
बस कंप्यूटेशन अलग हो जाता है, बस रिजल्ट तो सेम ही रहेंगे।
रिजल्ट सेम ही आएंगे, मोरल सेम ही आएंगे। हो सकता है कहीं कुछ चीजें आप नेग्लेक्ट करते हो, तो फिर उससे थोड़ा सा फर्क पड़ता हो।
ओके, तो कुछ लीड इंडक्टेंस का भी पैरामीटर आपने कंसीडर करा था? लीड इंडक्टेंस का?
लीड इंडक्टेंस नहीं, वो उतना मेजर इम्पैक्ट नहीं डालता है कंट्रोल के पॉइंट ऑफ व्यू से। अगर आप देखो बहुत ही ज्यादा हाई परफॉर्मेंस सप्लाई है, तो फिर ये सब चीज इतना, ऐसे तो कैपेसिटेंस भी होता है, जंक्शन कैपेसिटेंस मॉसफेट का अंदर, वो भी कंसीडर करते हैं, बट वो इतना इम्पैक्ट नहीं डालते हैं नॉर्मली। बहुत ज्यादा हाई परफॉर्मेंस सप्लाई होगा तो ऑब्वियसली वो भी कंसीडर करना ही चाहिए। Any other doubt, please? Anyone else?
इससे रिलेटेड आप जो कंट्रोल डिजाइन करेंगे वो भी आप शो करेंगे ना इससे रिलेटेड, कि आप व्हेन यू आर डिजाइनिंग कंट्रोल बाय कंसीडरिंग पैरासिटिक एलिमेंट्स एंड व्हेन यू आर डिजाइनिंग कंट्रोल बाय नॉन कंसीडरिंग।
हाँ, मैं पैरासिटिक के साथ ही करूंगा, है ना।
अच्छा,
पर हाँ, उसका कंसेप्ट के हिसाब से क्या फर्क पड़ता है, दैट आई विल डिस्कस इन स्टार्टिंग, राइट।
ठीक है।
व्हाट इज द इम्पैक्ट ऑफ दैट, आई विल टेल।
So from my side, I am done, sir. Thank you.
Okay, thank you. So I think I stop here now. This is the time for quiz. AICT host Anupam and Bhupesh. Are there?
Yes, sir.
So what is the instructions for this quiz?
Sir, we have to just
stop
publish
recording. Class is over, so you can stop the recording.
Okay, sir.
So what is the instructions for this? You can brief them.
Sir, we just have to publish the quiz. It is ready.
So once you publish, it will be available in their Canvas platform, right?
Yes.
And they can access it maybe now also, or maybe after some time. But once they start accessing, then they have to finish it, right?
In 30 minutes, yes, sir.
In 30 minutes, whenever. Means if they start now, then they need to finish now. right?
There is 2 days time.
29.
So means by tonight or tomorrow,
So till 29th of June.
means by Sunday, है ना? So okay, so the thing is that by Sunday you can complete this quiz. You may access it today itself, and you may also but whenever you start, you have to finish it. So whenever you get time properly, you can revisit the things and all, and that time only you please attempt it. And it is mandatory quiz 1 and quiz 2 to attempt it, and whatever score you get. So certification purpose, we need it. So you can publish it now. How many questions? 30.
30 questions, sir.
30 questions, 30 minutes, right?
Yes, sir.
So you can publish it now, and they can attempt it,
Done, sir.
because the time allotted for this is this half an hour only. And please be connected at least for up to 4 o'clock. If even if you are attending or not attending, keep your this session on up to 4 p.m. at least.
All of you, please check your Canvas account. The quiz is available.
Yes, please once check and let us know at least few of them that it's available there.
Hello, sir. I want to ask one question more. Uh, Hello. So we can leave now.